So in this exam, or in this video, we are going to go over the practice exam A for geometry, similarity and right triangle standards 6 through 8. Starting off, we're just going to run through questions number 1 all the way down through question number 11. In the first question, we are given two quick sketches for these right triangles. And we are asked to say, or rather asked to explain, why is it that opposite of theta over hypotenuse is the same in both? Or rather just show that they are the same in both. By far, the most common mistake people made with this was to discuss why the triangles were similar. There were a lot of explanations that said the 90s are matching, the thetas are matching, because of angle, the triangles are similar. And there were some other ones that had said because they have these three ratios for side, 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 some people use side, side, side similarity and said, I know that these triangles are similar. Well, similarity is of course relevant to this, but ultimately what we're trying to say is why is it, or rather show, this thing on the left is the same as on the right. And one very quick, very easy way of doing that is to say opposite of theta over hypotenuse on the left triangle. Well, which side is opposite of theta? Yeah, that's our bottom side, the 6. What is the length of the hypotenuse? So we'd have 6 over 10, and if we divided it out, we'd get the fraction 3 over 5 when we simplify. Well, do the exact same thing for the right triangle. Opposite of theta over hypotenuse. Opposite is 30. The hypotenuse had length 50. And so if we divided it out and simplified it, we'd get 3 over 5. So why is opposite of hypotenuse the same on both triangles? Because both of them, in this specific example, boil down to the ratio 3 over 5. Which we could write up as a sentence by simply saying something along the lines of, note that both triangles have opposite of theta over hypotenuse be equal to 3 over 5. And there we're done. Obviously, this is not the only correct way to write it up. Other people observed that they both simplify to the fraction 6/10. Some people turned them both into their decimal format and said the decimals match up. They're all based on the same idea of saying, if you take this opposite over hypotenuse, it's the same number, just written in a different way. Now, when you have your retest, are you going to get the exact same problem? Of course not. Are you going to even get the same triangles? Probably not. I can give you two different triangles that are still similar. And instead of saying opposite over hypotenuse, you could have opposite over adjacent. You could have adjacent over hypotenuse. We could pick whatever ratio we'd like and simply say, show that this ratio is the same in both of them. The triangles could be different, the ratio could be different, but the intent behind the problem is still the same. If you take the specific numbers and put them in, you can see that it's the same thing, just written in a different way. Okay, continuing to our next one that we had, and I'll extend this further. We would have, our I can statement is use the relationship between sine and cosine of complementary angles. And so we're told cosine of 20 degrees is actually about 0.93969, and it's going to, of course, keep going. Name another trigonometric identity or trigonometric function that has the same value. Well, if you know the fact that, yeah, the work is really easy. Cosine can be changed to sine as long as you subtract that other angle off of 90. So there's no work at all. It's just sine of 70 degrees. You're done. If you know that fact, the work itself is just instant. Now, of course, am I going to give you the exact same thing? No, I could very easily just say, make this the cosine of 75 degrees. Give me something that's the same as cosine of 75. Okay, cosine gets changed to sine, and the angle would be 90 minus 75. So you'd have sine of 15. And I don't even have to start with a sine, or I'm sorry, a cosine. I could say sine of 30 degrees. Give me something that's the same as sine of 30. Cosine of. So there we go. Really quick, really easy. You just change the sine and cosine, but you also change it to its complementary angle. Just subtract the angle off from 90. That's it. If you know that fact, the work is just instant. If you don't know it, you're kind of SOL. The second part of our standard number 7 is to explain why that fact is true. That first part's just kind of using it, knowing it. Second I can statement is explain why it's true. And we use the specific example of explain why the sine of 20 degrees is equal to the cosine of 70. Well, I'm going to start by drawing a picture. And my picture's too tall, so I got to try to fix that a little bit. And understanding that it's not a perfect drawing, I'm not looking for perfection, but just something that's ballpark reasonable. Here is my drawing that has a 20-degree angle and a 70-degree angle. And we're asking, why is it that sine of 20 degrees, which is opposite over hypotenuse, why is that equal to cosine of 70 degrees, knowing that cosine is adjacent over hypotenuse? And there are a lot of ways that we could write this up. There are a lot of things that we could do to basically explain it. Perhaps the best one that I saw a student turn in was this observation. Since we're looking at sine of 20, I saw people say x, y, and h, just giving them names. But then they also wrote in, this is opposite of 20 degrees. It's adjacent to the 70 degrees. And it just leads us to the observation that sine of 20 was x over h. Adjacent of 70 is x over h. And so it's very easy to see then x over h is equal to x over h. The most common answer that people had was it's two different ways of writing the same thing. And yes, that's true. But that could just be like a memorized answer that doesn't show that you actually understand it. It's two different ways of saying the same thing requires more details. What do you mean by two different ways? Having the picture, having this other detail, those details show the full understanding besides it's two different ways. It's true. Opposite of 20 and adjacent of 70 are two different ways of referring to this side length x, but with more detail, it shows that you actually understand that instead of just memorized an answer. Now, are you going to get the exact same thing on another one? No. We don't have to make it 20 and 70 degrees. There's nothing special about 20 and 70. The standard is complementary angles. So if we were to change this to be 40 degrees and 50 degrees, does it really change anything? The ideas are still the same. It'll be opposite of 40 degrees and adjacent to 50 degrees. Or we could say 37 degrees and 53 degrees, 11 degrees and 69 degrees, 79 degrees, not 69. But basically, that's it. You got to have something like this, writing it up and provide some details. At this point, I'd like to remind people, do you remember all the stuff that we had written on the board? Where for your notes before the exam, we'd mentioned write this stuff down for your note cards, that way you've got something to reference about how
High school students that are going to write the test.
Well, those pieces that we had written on the board for our notes, they just go back to referencing the idea that we need to have, basically it's just our list of skills. The next piece we're going to be looking at are all those problems for standard number 8. The problems, the word problems. Of course, you're not going to get the exact same problems with the exact same picture, or even the same picture with different numbers. But the list of skills is still the same. We had problems that said, I need you to find out an angle using inverse sine, inverse cosine, or inverse tangent. Our list of skills, find an angle using inverse sine, cosine, tangent. Find a side length using sine, cosine, tangent. Find side lengths based on Pythagorean Theorem. Completely solve a triangle. Figure out word problems. That list of skills are still going to be on there. It's not going to be the exact same problems with the exact same pictures or just the same pictures with different numbers, but the skills are still going to be checked. You know that there's going to be a problem that's based on figure out this angle. You know there will be problems based on figure out this side. And there could be different ways of doing it. Just because we are solving one particular problem does not guarantee that it's going to be the exact same strategies before. For example, we would continue this next one with number 4, how we were given a picture here, and we were told, figure out this angle. Okay, Dante right away made the observation that we have opposite, we have adjacent, and we have the angle, which lets us build it to say tangent of the angle is opposite over adjacent. And Dante immediately noted, in order to get rid of tangent, you'll take the inverse tangent, which led us to what we would need to type into our calculator here. So yes, we will have problems that say, figure out this angle. Is it going to be this picture? Of course not. Does it even have to be an inverse tangent problem? No. We could give you the same type of problem where you're given a leg and a hypotenuse, and you would have to use sine or cosine. It doesn't have to be tangent, it doesn't have to be sine, it doesn't have to be cosine, but all three of them are based on the same set of skills that you recognize this as an inverse problem. Inverses give you the angle. Now, having enough time, I put this into our calculator, and the direction said to round to the nearest tenth, which wound up being 28.8 degrees, and there we're done. It is certain you will have problems based on this skill. You will have to know how to set up and solve an inverse trig problem. Not this inverse trig problem, but any inverse trig problem. It's based on skills, not problems. Our next one was built similarly. For this one, figure out the length of this value x. Now, in this particular problem, we have to look at it and say, which pieces do we already have? Which pieces are we looking for? And I got to rewrite this because I copied the problem incorrectly. It wasn't just...
Can you have Braxton Flynn come to the office, please? Can you have Braxton?
And I had copied this one incorrectly. This was actually given to us as a 28-degree angle. All right, now looking at this one, of course, we have the angle. We have the adjacent side. We have the hypotenuse. Adjacent and hypotenuse form cosine, so we'd have cosine of 28 degrees is the adjacent over hypotenuse, and we have to solve this. The most common error that people made on this particular problem was multiplying by 29.3. Yeah, you're right, Dante. We're not supposed to multiply by the 29.3 because this is a problem that is set up divide by x. The only way to get rid of the division is with multiplication, but it has to be multiplication by the x. So when those pieces cancel each other out, we're left with our next stage with dividing by cosine. And so at this stage, we get the correct answer, 29.3 divided by the cosine of 28 degrees. And the most common mistake is people actually turn that into multiplication. They took 29 multiplied by the cosine. When we enter this one into the calculator, we get rounded 33.2, and the label should have been miles. And I'll scroll this back up. Continuing to the back side, we're given this drawing, or rather, a more precise version of this drawing instead of my quick sketch. And we were asked, completely solve this right triangle. So find everything. Well, what are the three pieces that right now we don't know? We need to know the measure of angle A and the two side lengths. Knowing that we were told round, well, we weren't even told to round anywhere. So without further instructions on where we should round, we can kind of round wherever we choose as long as we're using the approximate symbol. So where would you start? What's the easiest thing to get? Angle A, which we could get by subtract off from the 90. And so there's our first piece. That's a 37-degree angle. Okay, now what? We can kind of pick and choose which one we'd like to do. Do we want to go get AC next, or do you want to go get BC next? You get to choose. Okay, Dante spoke up first and said he'd like to get BC first, which means that's the adjacent side. Knowing, of course, that we already have the hypotenuse based with our angle, this is the same type of thing as what we just finished. We can set that up and note that the cosine of 53 degrees is the adjacent over hypotenuse, which of course gives us something to solve. We could just take that, multiply by 5. So BC is equal to 5 times the cosine of 53. And since we were not told to round, we could just leave it right there. That is the exact value. We also could put it into our calculator and round it. When we put that into our calculator, BC is about what value? 3.01. Okay, so 3.009. That is so incredibly close that why don't we just say 3.009 is about 3? Which leads us to our last piece. We've got to get the value of AC. And of course, we could do something else like that. We could use sine of 53 degrees to get AC. We could use cosine of 37 degrees to get AC. But we could also use Pythagorean Theorem. With this particular one, my choice is just to use Pythagorean Theorem. Although I know other things would work, this is the one I'm picking to use. So my leg, we had a 3. My hypotenuse is 5, so we've got to solve that. 9 plus legs squared is 25. So subtracting 9 from both sides, legs squared is 16. Taking our square root, we get the leg is 4. And so there we go. We have all 3 pieces. Now please note, this particular problem was solve the right triangle. If I give you another problem, is it going to be the same thing? Well, definitely not the exact same problem, but it could be quite different in that this is a problem where we were given the hypotenuse and given an angle. How would it have been different if we had leg and angle? How would it have been different if we were given leg and leg? Or if we were given hypotenuse and leg? We would have wound up needing to do different things. If we were given hypotenuse leg, we could use Pythagorean theorem to get the third side. Or we could use an inverse trig function to figure out an angle, and then use trig to figure out other pieces. Depending on what strategies we pick, there are lots of different ways that we could have answered this. And of course, with different starting pieces, you're going to have to use different strategies. Don't just instantly assume that you have to start by getting an angle, because what if you're not given an angle? Okay, extending further. Next one. What is the exact value of cosine 45 degrees? I have to admit, these ones made me more mad than anybody else when I was grading them. Because I remember saying in class, stressing heavily, you cannot get the correct answer for exact from a calculator. By far, the most common answer that I saw on this was 0.707, and people kept writing more digits past that, but that's still a rounded answer. It was rounded to 10 or 12 decimal places, however many spots your calculator gives you, and rounded to 12 decimal places is not exact. You could round to 50 million decimal places, and it's not exact. The only way that you're going to get the exact value is by using our special right triangles. And I remember putting them up on the board and saying, by the way, you'll want to take and write these pieces down because you will need them. Whether you memorize them, which frankly you should do, they're that important, or you have these pieces written down for your notes, you need to be able to recognize this information, which we had built and further gave the equation. The leg multiplied by the square root of 2 will give you the hypotenuse. So with this particular one, what's the exact value for cosine of 45? Cosine is adjacent over hypotenuse. So you pick a 45-degree angle. What's the adjacent leg? What's the hypotenuse? You're done. That's it. 1 over the square root of 2. And for some reason, a lot of people wanted to try multiplying by 1, and they wound up saying the cosine of 45 degrees equals square root of 2 all by itself, and that was a mistake. I don't understand what they had done, but that's it with the purple. So given how immediately instant, just that problem is an instant piece if you know the drawing, it really bugged me that people didn't get that one correct because it's such a simple problem. As long as you've got notes, as long as you know the triangle, and I know I went crazy overboard with saying, write the stinking thing down, you will need it. Same thing with our other special right triangle, the 30, 60, 90. Because when you have a retake, it does not have to say cosine of 45 degrees. It could very easily say sine of 60 degrees, or tangent of 45 degrees, or sine of 30 degrees, or cosine of 60 degrees. But it's still based on the same set of skills where you need to know the 30, 60, 90 triangle looks like this, and I'll have to extend the page. Short times the square root, short times 2 gives you hypotenuse, and the short leg times the square root of 3 equals the long leg. We had those written for notes. Now our next problem goes through and says, what are the exact side lengths if you have a hypotenuse of 12? Well, there's a couple ways that we could do that one. The first is with the equations. If we know the hypotenuse is 12, what is the short leg? 6 times 2 gives you 12. So there, we know the short leg is 6. And if the short leg is 6, what's the long leg? 6 times the square root of 3. I'm not sure why, but the most common answer people had there, besides using a calculator, which does not give you exact, but a lot of people gave me the answer square root of 18. And I have to assume that they just took 6 times 3 to get 18 and put the square root inside, breaking a lot of our square root rules. We know that we can't do that. You should have just left it alone and said 6 times square root of 3. You're done. Now, that's not the way I would have done this problem. To me, there's a faster, easier way. Let's use similar triangles. If my hypotenuse is supposed to be 12, how do I turn 2 into 12? Times 6. So my scale factor is times 6. Just take both the legs times 6. 1 times 6, 6 times square root of 3. I'm done. Just that fast. Okay, so continuing from there, our next one, a diver is swimming at a depth of 63 feet. He sees a buoy floating at sea level at an angle of elevation of 47 degrees. Okay, so we've got our diver right here. We're told an angle of elevation of 47 degrees to get up to this buoy at the surface. So there's the surface of our water. Obviously, that's still another 63. And we were told our angle of elevation is 47 degrees. Remember, the angle of elevation or the angle of depression are always made with where the current height is. And we're wondering, how far must the diver swim so he's directly beneath the buoy? Well, since the buoy is floating on the surface, we mentioned that because of potential ambiguity, we mentioned in class that directly beneath the buoy means right at the buoy, right underneath it at the water's surface. So if you've got the diver currently down here and they need to swim up there, this is the path that we have to find. The most common error people made was not in the drawing, because people did a fantastic job of creating the drawing. They showed great understanding there. And even the solving part people did really well on. The most common error was that people found that one. And we did mention to be directly underneath the buoy, we meant the problem intended directly underneath, right at the buoy. And so they just found the wrong side length. All the work was correct, but they got the wrong piece of information. For this problem, we would have to recognize we had an opposite, we had hypotenuse, we have the angle. With opposite and hypotenuse, that tells us it's a sine problem. So we would have had sine of 47 degrees equal opposite over hypotenuse. And we have seen already that when we wanted to solve that problem, in the end, it turns into this component. Plug that into your calculator, round to the nearest foot, you have your answer. If I remember correctly, I think it was 86 feet, or my memory could be off. Plug it into your calculator, round it to the nearest foot, and that's the end of the problem. Our next one is this Tour de France problem. The major part to this one is we are told a section of the Tour de France has an 8% grade. If you understand what 8% grade is, this is a problem that's actually fairly quick. How do you write 8% as a fraction? Yep, 8% as a fraction. Percent means per 100, so put it over 100. And so if we've got an 8 over 100 grade, it's really helpful just to remember that grade is just another word for slope. So if you have a slope of 8 over 100, that lets us create the drawing rise over run 8 over 100, and we were asked to get this angle theta. Well, how do you get angles? Inverse sine, inverse cosine, inverse tangent. So which one do we have? Inverse tangent of 8 over 100 gives us our answer theta. Since the directions told us round to the nearest whole degree, plug it in the calculator, and we'd get the measure of angle theta is about 5 degrees. We're done. And the last problem we had was the space shuttle problem, where we were given this particular drawing. This was an angle of elevation of 16 degrees. That was an overall angle of elevation 74 degrees. And the word problem goes through to describe this person starts watching the space shuttle, and when they first see it, it was already at an angle of elevation of 16. And when they lost sight of it, it was up at an angle of elevation of 74. How far did it travel while they were watching? So we had to figure out this piece in yellow based on the fact that this bottom length is 1 mile. Well, for a lot of people, I wound up putting down these 3 points just as a frame of reference. So that way we could say this length of AC is the overall length AB minus that tiny little piece at the end of BC. And so that was our strategy. we have to figure out the length of AB, we have to figure out the length of BC, and once we have those two lengths, just subtract. Now, in order to do that, please notice that if we're looking here at BC, that piece is opposite of 16. 1 mile is adjacent to 16, which tells us then that tangent of 16 is opposite over adjacent. Dividing by 1 doesn't do anything, though. So we wind up with that little piece of information. BC is the tangent of 16. When we're looking at AB, AB is opposite the 74-degree angle. This bottom piece of 1 mile is also adjacent to the 74-degree angle. And the exact same way, we wind up with tangent of 74 degrees is opposite over adjacent, which led us to the conclusion that this piece had to be the tangent of 74 degrees. And so this is the exact value. But we were told to round this answer to the nearest tenth. So plug that into your calculator. Tangent of 74, subtract the tangent of 16, and when you do that and round it, it gets to be about 3.2 miles. And you're done. It wasn't a very common mistake, but one thing that people did, a couple people got the tangent of 74 and rounded that. Then they got the tangent of 16 and rounded that. When they did their subtraction after the fact, they didn't wind up with 3.2 because rounding early in the problem actually compounded the rounding error, and they wound up with like an answer of, I think, 3.4 or something like that. Just because one of them rounds up, one of them rounds down, and it just turns out to be weird that the rounding early causes errors. Round at the end of the problem, not the middle. The other common mistake people had, there were a lot of people who got just the tangent of 74 and said that was their overall answer. And they never subtracted off the piece at the beginning that they didn't see. My suspicion is that they didn't read the problem carefully enough to understand which piece they were trying to find. But that finishes off number 11. Yep, that was the whole exam.